Okay, Happy New Year, everyone. We are at the 53rd meeting of New Directions in Group Theory and Triangulated Categories. And today our speaker is Šťovíček from Charles University, Prague. And he'll be talking to us about mutation, T-structures, and torsion pairs.
Okay, thank you very much. So I hope you can all hear me well. Yeah, it's a joint work with Lydia Angeleri, Rosie Laking, and George Vittoria in this archive code, and it's a little bit technical. So I'll try to give you some motivation. I mean, why I was interested in, or why we were all interested in such things. So maybe the concrete motivation actually starts with quite specific triangulated categories. So it's about and then torsion pairs, right? Torsion pairs for finite-dimensional algebras. I think maybe the important paper there, where which goes in the direction, is the one by Demonet, Iyama, Reiten, and Thomas, roughly 5 years ago. And they start with the following setup. So they start with a finite-dimensional algebra and finite-dimensional modules, and they look at torsion pairs, right? So I guess you all know what a torsion pair is. So it's a torsion, it's a pair of two classes of modules. And okay, there are no morphisms from left to right, and every module, has a maximal torsion part and a torsion-free factor, right? And these guys, actually are given by closure properties. So in that case, a class is a torsion class of some torsion pair. So this T, if and only if it's closed under, I don't know, it's closed under factors and finite factors and extensions. Okay, so and so because it's given by closure properties, given any set of modules, there is a unique smallest torsion class containing them, and therefore these guys form a complete lattice. We can order the torsion class by inclusion, and we have a complete lattice of torsion classes. And these 5 authors studied this lattice, and they proved various properties. And okay, why you might be interested in that? So there are basically 2 reasons. One, some kind of general interest. These are frequent structures, and something rather basic, right? But then these people were also interested for another reason. Because it's closely related to cluster theory and generalizes some result from cluster categories and the combinatorics introduced by Fomin and Zelevinsky some time ago, maybe 2 decades or so. And so, okay, in that case, we may restrict attention to some torsion pair classes, which are special and which were relevant for the cluster combinatorics, and then Demonet and the others try to generalize this to all torsion classes or torsion pairs, right? So we can call a torsion pair functorially finite if there exists some module P, such that every other x in the torsion class is a factor of finite direct sum of copies of P. So this is not the original definition of factorially finite, but in this case it's equivalent. So everything is controlled by one module, and this module can be actually taken rather specially. It can be x-projective. It can be such that there are no extensions from P to any other object of T, right? And P itself is in T. So it's something like the projective generator in the exact category of T. Actually, it will turn out to be such a thing, even though it's not written up, all the conditions there, and the thing is that because we are working with finite dimensional modules, so we have some nice properties. So every module decomposes into indecomposables in an essentially unique way. So if we choose P such that it's just a direct sum of non-isomorphic indecomposable summand, then there is unique such P up to isomorphism. And this P was actually something related to cluster algebras. And then there is, by some older work by Auslander and Reiten, there is a unique correspondence between P satisfying some properties and functorially finite torsion classes. Actually, this was made precise and made maybe extended to this present form to Adachi, Iyama, Reiten in the tau tilting theory. But one point, I mean, in cluster combinatorics is this mutation. That I mean, you take one object like here an indecomposable summand of P and you replace it by another, right? And so you basically take such a P coming from above, from some torsion class, having this property, and you take it out. So you factor it out, this summand, and you replace it by another summand. And it again comes from another torsion class of this type. And the point is that actually it's very close to the original one, right? I mean, so there is an arrow in the Hasse diagram of the lattice of torsion classes. So this torsion class T prime is bigger, but there is nothing than T, but there is nothing in between, properly in between them, no other torsion class, right? And so, I mean, schematically, I sometimes depict them in some diagrams. So, I mean, maybe I try to explain them. So, I mean, I try to draw these in pictures. So basically, I draw this square for the module category, and the dots there could be modules, and it's of course imprecise, but if I try to draw a torsion pair, I view it that there are no morphisms from left to right, so there are only morphisms from right to left in the picture. So okay, for this purpose, this is good. You can imagine it like that, and then you have this torsion class T and the corresponding torsion class F, and they have essentially empty intersection. Well, of course, the zero modules are inside. And then you have some bigger T prime and smaller F prime. And what controls and what is interesting, I mean, you intersect the two bigger classes, the bigger torsion class and the bigger torsion free class. And it turns out there is actually that this intersection has a very simple structure, right? There is a single so-called brick, which is a module with trivial endomorphism ring, whose endomorphism ring just is a division ring. I mean, it's something like a simple, right? I mean, every non-zero endomorphism is an isomorphism. Every module in the intersection, okay, the modules in the intersection are precisely those filtered by S, okay? And so basically what you can say that T and T prime essentially differ by S. I mean, if you take T prime and you add S and you take the smallest torsion class, you get T prime, and in the same way F and F prime differ just by this S. And this was known for this for these functorially finite torsion classes, but actually one point of this DMMRT paper was that they proved that for all classes. Whenever you have two torsion pairs, and actually they are related by an arrow in the Hasse diagram of the lattice, so then I mean there is such a brick such that the intersection is filtered by the brick, and they basically differ just by that brick, right? Okay, so the question, I mean, just kind of one way to get to mutation in our context is continuing this line of thinking and asking, okay, so for functorially finite torsion classes, we have a mutation. We had some X projective generator and we replaced one summand by another, right? And as a kind of coincidence, I mean, the torsion classes also differed by a simple. But okay, now we know that if we have a Hasse diagram, such torsion classes always differ by a simple, by a brick. Not by a simple, by a brick, but is this an instance of some kind of mutation? Do we replace something like we did before, one X projective by another? And if so, the question is a mutation of what? Of course, I mean, because if the class is not functorially finite, we may have no non-zero X projectives at all. But actually, it turns out that it is an instance of mutation, and I'll try to explain that. And it goes to some kind of spectra and so on. So hopefully it will be in some form interesting to you. So first, in order to, I mean, get the problem into the right context, so then or right for me, which is a tilting theory, some form of tilting theory, but it's also related to some work, or very closely related to some work by other people, like some kind of derived injectives. I'll get to there in a moment. I will need to translate the problem to the language of T-structures. So closer to the title of the seminar, right? So again, I guess everyone here knows what a T-structure is. So I mean, the definition is here basically for me to fix notation and also to somehow stress that it's very close to a torsion pair, but in the language of triangulated categories. Okay. So here is the conventions which I'm going to use. I mean, maybe, I don't know, they're slightly unusual maybe, or could be for some of you. So I view really T-structure as a torsion pair. So I really will have U, which I will usually call the aisle, and V, which I will call the coaisle, and there is no, I will assume there are no homomorphisms between them from U to V. So if I want the heart, I need to shift one of the classes, right? So I mean, this is really U and V do not see each other, or there is no morphism from U to V. So if I want the heart, I will need to shift one of the classes by one, and I will shift U so that the heart will actually live in the coaisle, in the right-hand side class. Okay, so the heart for me will be U shifted by -1, intersected with V, and this will be this is an extension closed abelian subcategory of the original triangulated category. Okay, and the question is how to relate torsion pairs and T-structures, and this, I mean, goes back probably at least to Happel-Reiten-Smalow, and it's Happel-Reiten-Smalow tilting of T-structures. So that's also some kind of modifying T-structures. So what is the business there? So I have some picture for that. I mean, which is good for me. So so I will start with an original T-structure UV, which just a little bit later on will be the, say, the canonical T-structure in the derived category of the module category I originally was talking about, right? And I will take a torsion pair in the heart, and I try to modify the T-structure, and this is always possible. So so I will have I can take the class U star T, and this means, as is quite often denoted, like all objects X in D, such that there exists a triangle U in U, X, T in small t, and U1, right? So basically extensions of T by of U by T, right? And the same here in the second class, right? And so in the picture, I mean, depict the derived category like that. For simplicity, I will no, now it's not quite correct, I think. Sorry. So for me, no, it is, but sorry, there is something wrong with the conventions which I have there, I think. So I want like view that shifting by 1 means moving to the left, shifting by -1 means moving to the right, and homomorphisms, at least when as much as I'm concerned, should go in general from right to left and not in the other way around. Okay, so then I have this U, and I have U shifted by 1, and I have V and V shifted by 1, and the yellow part, I mean, it's the heart, and it is the intersection of U -1 and V, right? And inside I have a torsion pair, and then I add the torsion part to U and the torsion free part to V, and I have a new T-structure. I mean, where it is actually a T-structure. I mean, one can prove it formally, and the aisle will be this one, right? And the coaisle will be that one, and because it's right of the original one, I will call it later in some specific cases right mutation. Okay, and not only because of that, there are also other reasons. Okay, and then now the promised special case, I mean, right? So if we have, say, the finite-dimensional algebra, we can take the bounded derived category, and we can take the canonical T-structure, and then every torsion pair induces another T-structure, right? This one modified by the torsion pair. So actually, what one can prove is that torsion pairs in mod A correspond precisely to T structures in DB mod A, which are sandwiched between the canonical T structure and the canonical T structure moved by one, right? Well, actually -1 here, so one to the right in my picture, okay? So actually, instead of talking about some torsion pairs, I can talk about certain T structures, right? And T structures will be actually the guys which will be subject to mutation. And the goods, I'll get there in a second. Why I need T structures? Because I need to pass to the derived category. I will need some cosilting objects which will be derived injectives to some T structures. But okay, I'm not there yet, because what kind of T structure, right? This hard has no injectives in general, and I would need some hard with injectives. So the answer there, I mean, is that that I cannot just stay with finite-dimensional modules, right? I mean, this is the same story as with geometry or for commutative Noetherian rings. So the small module category of finitely generated modules over, say, a commutative Noetherian ring, or the category of coherent sheaves on a, say, some Noetherian scheme. So this doesn't have enough injectives typically. You need to go to quasi-coherent sheaves. So I will not somehow by the situation, if I want to keep things classical, I will not mutate projectives as before or some X-projectives, but injectives. So passing to the dual side. And I will get injectives as long as I will change the perspective from small modules to big modules, right? And this has some advantages, because I mean, essentially, say the heart will be always a Grothendieck. No, not essentially, really. The heart will be always, in my case, which I'm interested in, a Grothendieck category, and this has enough injectives. And in the cases I'm interested in, there are enough indecomposable injectives, and so it's like. And the set of isoclasses of indecomposable injectives forms a spectrum with some kind of topology. Okay, so for commutative Noetherian rings or for categories of quasi-coherent sheaves, the indecomposable injectives really correspond to points. So, so there will be some topological space, some points, which in some cases is really a classical one. Okay. And so what I actually do is the following. So in my example, instead of, or in my situation, instead of looking at small modules, I will look at big modules, or all modules, infinitely generated possibly, right? And if I have a torsion pair in the category of small modules, then I take the direct limit closures of the two classes. So I take actually, even in a naive sense, I take all direct limits of objects from small t and all direct limits of objects from small f, and then I get some capital script T and capital F, and this this pair is again a torsion pair in the big module category, right? And actually there is some lemma which is in a paper by Bill Crowley-Bowie, but I don't know, maybe it was known before, I don't know that, which says that actually this torsion-free class is special. It's closed under direct limits. So any direct limit of torsion-free objects is a direct limit, which is not automatic because this is a colimit construction. And actually all torsion pairs in big modules where f is closed under direct limits, sometimes these torsion pairs are called torsion pairs of finite type, actually all are in bijection with torsion pairs in small mod A, right? So they are all of this form. And I mean, the torsion pair in small mod A, I mean, you can get it easily just by intersecting these two. You can get it back, but by intersecting these classes with just small modules, right? So, okay. So, just some kind of upshot. I will be interested in some torsion, some T structures actually in the big module, in some T structures in the unbounded derived category. Now, okay, I have to also enlarge the derived category. So unbounded derived category, sandwich between the canonical T structure and its -1 shift, right? And the T structures will have to have a further property that they are modified, that they are Haptorite and small tilted, using a torsion pair in this way, but using a torsion pair where the torsion-free class is closed under direct limits. Okay. And so what I get in this case? Okay, so now just a bit of hand waving. So I will get certain T structures, say in the unbounded derived category, right? So for me here, D will be the unbounded derived category of mod A. Okay, so of course this is not just a triangulated category. This is some enhancement. I mean, whatever you like. I mean, it's not so important. But the thing is that, I mean, in that case, this right-hand side class of the new T structure is actually closed under homotopy, directed homotopy colimits in the derived category with any reasonable enhancement, right? So what we get is actually a T structure which where Lurie calls the isle something like a Grothendieck pre-stable infinity category. So some kind of Grothendieck-like T structure, okay? And so this appears in the work of other people. For example, I don't know if I think Francesco Genovese spoke in this seminar, right, not so long ago. So he also studies this T structure, but from the perspective of DG category. So this is certainly an object which people were interested in, right? So I'm interested in such categories, and in that context, actually, I can speak of mutation, but mutation of derived injectives. And what are these derived injectives, right? Okay, so if we have such a T structure, then the heart is a Grothendieck category, always. So it has enough injectives, but actually it's not, injectives in the Grothendieck category are not good enough. I need derived injectives, which means X injectives in the coil F star say D greater than 0, right? And X injective means that of course X1 in the coil, okay, in the derived category. So that means home where the second argument is shifted by 1, right? D greater than 0, and of my object I, which I'm interested in. So X injectives I, so this should be 0, okay? The good thing is that actually these X injectives, I mean, they live in the coil, not in the aisle, but there is a fact, a standard fact, which is again appears in the literature several times, that the homology functor with respect to the T structure actually induces an equivalence between the category of injectives in the heart of this T structure here and my X injectives, right? X injectives in the coil. Okay, so this is a bit confusing. I mean, the X injectives are not in the heart in general, but they're actually equivalent to the category of injectives of the heart, right? And these are the guys, these X injectives are the guys which actually I want to mutate. I want to mutate this in the composable derived injectives, okay? And maybe before I get to the mutation itself, so let's make some comments like this mutation of these T structures or mutation of the X injectives. So these derived injectives, X injectives in the coil, they are appeared several times in the literature under different names. So they are called derived injectives, as I called them before. They are called injectives in presentable infinity, pre-stable infinity categories. So Lurie calls them just injectives in his spectral algebraic geometry appendix C, or they are called in representation theory of cosilting objects. So this comes from tilting theory. People modify this tilting long enough to get to this term cosilting. And these are essentially the same concept. So basically, just maybe writing the correspondence a bit superficially as a slogan. So a cosilting object is the same essentially as a derived injective cogenerator. say in the sense of Lurie or Genovese. I didn't order the names alphabetically here. Sorry for that. Genovese and Vandenberg. And basically, so what is it? You have such a T structure. If you want to stay down to the earth, you get such a T structure, which I have here. You take an injective cogenerator for the derived category and you pull it back via that equivalence when you know that it is an equivalence, and you get an derived injective cogenerator. And this is precisely what people call a cosilting object in that context. So, okay, from now on, my assumptions will be that D is compactly generated triangulated category, such as the derived category, with an enhancement always. I mean, it's really safe to stay with the derived category of a DG algebra or a small DG category. But the T structures I'm interested in are really those with T structures such that which are non-degenerate. That means the homological functor detects zero objects, non-degenerate, and this V is closed under directed homotopy.
Hi, Jan. I have a silly question.
Yes. No.
So do you require these compactly generated categories to be rigidly compactly generated, or just
no, I have no tensor products here. No tensor product here in general. It could be really something like what you can imagine is the derived category of, say, some non-commutative finite-dimensional algebra, for example.
Okay, thank you.
Okay, so no, not in general, just compactly generated. Okay. Okay, and now okay, let's get to this mutation. Okay, so now I know what I want to mutate. At least I want to mutate these derived injectives, right? And so I take two such. I mean, so sorry for using different variants of the terminology because once I'm saying derived injectives, one cosilting. Okay, I just try to keep this dictionary here. Okay, so the mutation for me, I mean, it goes basically to Iyama, because they studied silting objects, but cosilting is something formally dual. They studied it very generally. So I will take two cosilting objects, by which I mean I have two T structures of my type, which I just mentioned. These sigma and sigma primes are derived injective generators there, right? And the T structures may not be far, hopefully are not too far from each other. So I mean, it may happen that these which I would call, it should be script E, that the product closures, that means really the classes of derived injectives of the two T structures may intersect, right? They may have some non-trivial intersection. I'll give some examples soon. And okay, so in general, a right mutation says that, I mean, we have we say that sigma is a right mutation, sigma prime is a right mutation of sigma if there is some certain triangle where, okay, what is it? What is where? Maybe this is good. This is sigma itself. This is actually in the product closure, the closure under products and summands of sigma prime. Okay, and this one in the middle is in the intersection, and it actually so happens that I mean these two, right? The sum of these two is actually the product closure of that is actually again the same as the product closure of sigma prime. So this is actually a derived injective cogenerator for the T structure for sigma prime, right? And these two here on the right, I mean, this is a derived injective cogenerator of sigma, right? Okay, and this is a E cover, which actually means the same as this is sometimes called right approximation. Okay, So that means that any homomorphism from E to sigma factors actually through this morphism here, right? And it turns out the definition, I mean, looks technical and a bit strange, but actually in the end it's pretty well compatible with this change of these structures, because it will be again a haploidal small tilt with respect to a certain torsion pair again, and it's completely symmetric in the sense that this thing actually turns out to be E pre-envelope automatically. So a left approximation. Okay, so the two guys, the two derived these two say cosilting objects, so derived injective cogenerators are related by a triangle. Okay, but as I told, this is maybe not so enlightening. So let's try to unravel that. Okay, so just a second. Now I need to write it for you, because sorry for that, I didn't succeed to write it. So the one result from our paper actually characterizes this situation. Okay, so sorry, I just maybe want to see it in front of me so that I don't say something wrong. So okay, so start with so assume that D compactly generated, whenever needed, with some enhancements, and so now we have two T structures. So we have some, say, U and V with say derived injective cogenerator sigma and U prime V prime with derived injective cogenerator sigma prime. So then the following are equivalent. So one is, of course, that sigma prime is a right mutation of sigma, and the second is that actually there exists a hereditary torsion pair say SR of finite type. So okay, in the heart H of U of the first T structure. Okay, so what do we have, right? So I ask for a hereditary torsion pair of finite type. So the heart is a Grothendieck category. So the finite type here means again that R is closed under direct limits. The condition means sense, even though I don't assume now that the heart is actually something like a module category, just a Grothendieck category. But I have hereditary torsion pair of finite type UV such that actually this U prime is what? It's this U star S, and V prime is R star V minus 1. Okay, so it's really again the same situation here, as the same situation as it was here, just that the torsion pair is really special. It's hereditary and of finite type. Okay. And the second condition. Okay, so this is where we ask actually where we ask for a right mutation, right? We start with sigma and we try to see how actually sigma prime is constructed. And actually there is more than I say. I mean, I just characterize the mutation, but it's actually a theorem about existence. Whenever we take just one T structure and find a hereditary torsion pair of finite type in the heart, then actually there is another T structure and there is a sigma prime, which is that other T structure has again a derived injective cogenerator such that it is a mutation. Okay, so basically it says that these mutations are somehow related, very closely related to hereditary torsion pairs of finite type, at least right mutations. But we can also ask from the further perspective from sigma prime. So we also may ask for a certain torsion pair in sigma prime. So there exists now another T structure. So there exists a torsion pair S prime R prime in the heart of in the heart H prime U prime V prime of U prime V prime, sorry, in the heart of U prime V prime, such that, okay, it's not again a random torsion pair, it's actually funny. The condition now, it's again, the condition now is that S prime is closed under products. So that is a strange condition. But again, it basically says there is some hereditary torsion pair around, because what happens? If S prime is closed under products, it actually turns out, now I told something. Wait a second. This is not what I wanted to tell you. Apologies for the confusion. I'm always confused about that part because there exists actually not only a torsion pair and TTF triple, two torsion pairs next to each other, and I want so there exists this is the TTF. No, there exists a hereditary torsion pair. Sorry, there is again a hereditary torsion pair. Now it's what I want to say. Hereditary torsion pair. But again, now the extra condition on the hereditary torsion pair is actually that S prime is closed under products, which actually means S prime is actually itself a torsion-free class, not only torsion, but also torsion-free. So there is actually one more torsion pair in the game, which makes it confusing. But again, there is such a pair such that, and again, I mean, it's kind of again this Reiten small tilt, but now going to the left. So such that what happens that this U should be U prime shifted by one star S prime, and V should be R prime star V. Okay. So now this mutation of torsion pair is actually closely related, but now I mean the torsion pairs have to be hereditary, and before there were no heredity. This condition was not there. But okay, before I get back, before I get there, I'll try to show you some examples because I spend a lot of time with definitions, so I will show you some examples. And I can give you actually two basic examples where this happens. So first, D could be the derived category, say of say mod R, where R is a commutative Noetherian ring, right? But okay, I can choose a simple commutative Noetherian ring. Say simplest non-trivial could be simple non-Artinian, where it's maybe too trivial, would be a Dedekind domain. So I may choose, for example, the ring of integers, right? So this will be actually the derived category of abelian groups, right? And I can start with the T structure UV, again the canonical one. So say D less than 0 and D greater than equal 0, where I don't know where say the heart is just a category of abelian groups, And okay, so it has, of course, enough derived injectives. Derived injectives are just injectives. So this is in the case an injective cogenerator is Q plus Q over Z, right? And I may try to mutate it. And actually, if I want to, so write mutations correspond bijectively to what? To hereditary torsion pairs of finite type, hereditary torsion pairs of finite type in abelian groups. But actually these are quite easy because this actually always corresponds to, in any commutative Noetherian ring, to specialization closed sets, specialization closed subsets of the spectrum of R, right? And so basically what happens that we can replace any by mutation. So the mutations actually are such that we can replace any prefer group. So mutations. Okay, Q has to stay in any mutation where it is, up to one case where it's actually shifted by one. But the typical mutation is that we take an indecomposable injective, which is typically some prefer group, right? Some ZP infinity prefer, and it is replaced to the adic completion, to ZP to the adic group. I mean, use that notation. Okay, so basically the mutations are then really of that form that, I mean, yeah, okay, there was one thing which I forgot to say. I mean, we have another result which says that, I mean, if you look at indecomposable mutation, indecomposable derived injectives for one T structure and indecomposable derived injectives for the other T structure, so there is a bijection. And the bijection is either, I mean, some indecomposable injectives stay where they are, because, I mean, there should be some intersection of the two classes, and some indecomposable injectives, derived injectives, are actually related by such a triangle. And for the ring of integers, I mean, we can basically replace some prefers by some adics. So take the typical right mutation is that we take some collection of primes and replace some prefers by adics, and the rest stays. The rest is the intersection, right? And another example is where D is, say, the derived category of quasi-coherent sheaves of, say, the projective line, and that is basically a very similar. The situation is very similar. Okay. And now I should finish soon. So, okay, I'll try to get quickly back to the original situation, right? So what is wrong? Why now I have hereditary torsion pairs, and before in Artin algebras I didn't have them, and I even couldn't have them because there are too few, right, to get something interesting. The point here in this example is that actually the derived category of quasi-coherent sheaves in P1 is equivalent to the derived category of modules over so-called Kronecker algebra. So it's a path algebra if it's coherent projective line over a field K. So it's a path algebra over the Kronecker quiver, right? And now I'm actually viewing, so the hereditary torsion pairs actually appear when I view them from the perspective of coherent sheaves. But this is already a mutation. This is already a tilt of the category of from the category of modules, right? Over the Kronecker algebra. So actually, I need to change the perspective a little, and this is maybe the last thing which I managed to explain. So this will be about mutation of torsion pairs. And here the situation is actually like that. So say, for simplicity, D will be derived category of capital mod A. So all big modules where A is, say, a finite-dimensional algebra, even though it's more general, right? And the T structures structures, say UV and U prime V prime are given by torsion pairs in model torsion pairs TF and T prime F prime in mod A. Okay, so two torsion pairs in mod A determine two T structures, okay, which are sandwiched between two copies of the canonical T structure. And I may ask, and okay, if these torsion pairs of finite, if these torsion pairs are of finite type, then actually I'm in the situation I was talking about, right? So the corresponding hearts are then Grothendieck categories. They have finite derived injectives and so on. And now the question is, when actually U prime V prime is a right mutation of UV, so then I will say that, okay, TF is okay. So and okay, of course, in principle, because the T structures are given by the torsion pairs, so I can ask where T prime F prime, when the T structure corresponding to T prime F prime is a right mutation of the T structure corresponding to TF in the preceding questions. And it actually turns out that this was precisely what was studied implicitly, or I mean, it was equivalent to Demonet, Iyama, Reiten, Reiten, Todoro, who was the T. Sorry, I think, was it Gordana, Todoro? No, Thomas. It was Hugh Thomas. Okay, sorry. It was Hugh Thomas. Okay, right. And it actually turns out that I mean, the answer to what I wrote before, where is it? That actually the answer to this question is affirmative, but the torsion pairs have to be incompleted. They have to be inflated to big modules by direct limits. And you need to consider two hearts for the torsion pairs, and then this situation is really a mutation of when you have a Hasse, an arrow in the Hasse diagram is really a mutation of a single derived injective. So the two collections of injectives are really differ by a single injective. And in one of the hearts on the left, this brick S actually will become simple in that heart. And the injective will be an injective envelope of that. And only from the perspective of those two hearts, you see the hereditary torsion pairs, but the hereditary torsion pairs actually control the situation. Okay, so to conclude, the idea is that then really you get a mutation. You have some derived injectives in one heart. You have derived injectives for one T structure, derived injectives for another T structure, and there is a bijection between them as sets. And the mutation can be interpreted like that. But what we, for example, do not know, and I will conclude with that, is because there is a natural structure of topological spaces on both the sets of derived injectives. Why because there is a natural topology on the set of indecomposable injectives up to isomorphism for any Grothendieck category, right? Okay. And we do not know how the topologies are related in general, for example. Okay, but it's really, I mean, the game is a bit technical. So thanks for your attention. I think I will stop here. The game is a bit technical, but it really gives you some kind of refined picture about how you change one heart to another, and it was studied really. Equivalent problems were really studied by people in the field of finite-dimensional algebras and their representation theory. Okay, thanks a lot, and sorry for the mess at the beginning, the technical problems there.
Okay, thank you, Jan. Can we all unmute ourselves and give the speaker a round of applause? Do we have any questions for Jan?
maybe we do that.
I saw a hand. I don't know if that was a hand for a clap or like a hand that was like eager to ask something. I had a small comment to make. So if you just go back to the last page, well, I mean, to the page before the, the second last page. Yeah.
One.
I think one other example that could be very useful here might be, I don't know, derived category of quasi-coherent sheaves over, let's say, an algebraic stack.
Yeah.
Like this new work by like Hall and Reed and then Amnon, etc. I mean,
okay, I don't know too much about this, but okay, thanks. I mean, of course, one can get some further extension from quasi-coherent sheaves to stacks possibly. I don't know. I mean, whether it's straightforward or something goes wrong, that I cannot say because I know very little about this. Well, I can imagine. Actually, if you look at not at the Kronecker algebra here, but you have some time hereditary algebras, then you get some kind of stacks, right? I think so. Yes, so something survives, but there is more. But okay, at least in that case, it can be computed completely, I guess. So there is some geometric part and some non-trivial combinatorial part and some combination of those, at least in these for these simple stacks.
Sorry, was someone else asking something? Right. Okay, any questions or comments?
So you mentioned that what you maybe don't know at this stage is how the topologies would relate. Do you know some cases at least where that is maybe interesting, or do you have an expectation of how things would turn out in general?
That's a good question. So far, I think there is one trivial part of that story, I think, because I think there is some intersection between the spaces, actually it's a theoretic intersection coming from the common part, and that on that part, I think that the induced topologies should be the same. And I think for commutative Noetherian rings, for that example, I think it could be, I talked to some people, I think it could be extracted from the, I think that is probably the same, that it probably could be extracted from the literature, that I mean, really the bijection, the theoretic bijection we have is a homomorphism. But in general, I don't know, that's the problem. I lack examples which would be computed sufficiently in detail. Yeah. But that's future work, of course, that someone has to do.
Okay, thank you. Do we have any more questions? If not, let's thank the speaker again. So next week, I think we're supposed to have Bernard Keller as a speaker, and the video recording of this talk will be uploaded to the YouTube channel shortly. Okay, thank you all for coming.
Okay, thank you. Bye-bye.